Today let us discuss briefly about the RF integrated circuits. So RF integrated circuits are the systems which operate in the radio frequency range, normally ranging from 300 megahertz to 30 gigahertz. So the systems which operate under in this frequency range are termed as the RF integrated circuits. So now let us look at the few characteristics of the RF integrated circuits. Coming to the first one is the voltage gain and the power gain. Normally the voltage gain and the power gain are expressed in decibels for the RF systems, and they are given AV 20 log. Similarly, you have the power gain, output power by input power. So when you think of an RF integrated circuits, you normally look into the what are the non-linearities which we can look into it. So coming to the non-linearities, the first one is the harmonic distortion. What is harmonic distortion? So normally for a nonlinear system, you have a nonlinear system. So if you give an input pure sinusoid, the output consists of a frequency components which are not only the harmonics of your input frequency. Means like you have f, so 2f1, so 3f1, and so that, like if you have something like y of t is a1 cos omega t plus a2 cos square omega t plus so you have second harmonic and third harmonics. So you have to take care that the power of the harmonics must not be greater than the fundamental tones in your system. When you apply an input pure sinusoid to a nonlinear system, normally your output consists of a frequency components which are the harmonics of the input frequency. So the power of the harmonic components should not be more than the fundamental tone in your system. So this gives rise to an harmonic distortion. Let us see what is intermodulation. This comes into picture when you give a two inputs. Let's say you have given a two input sinusoidal pure with a slight difference. So the output is does not only contain the harmonics, they also have some kind of intermodulation. We call them as an intermodulation products which are not harmonics. These intermodulation products are either the sum or the difference of the input frequencies. So let us say if this is f1 and f2, you can have either f1 plus f2, f1 minus f2, and the harmonics of the f1 plus f2 and f1 minus f2, things like that. So those are actually called as an intermodulation products. Normally the characterization of the intermodulation is done by the two-tone test for an RF subsystem. Two-tone test. In this two-tone test, as I said, you have to give the two inputs with same amplitude, and you try to give this to the your system and try to calculate the power of the signal, power of the IM products when compared to the fundamental outputs. So, while doing this, you have to measure something called as IP3, third intercept point. This IP3 is normally calculated as, let's say you have an input power and this is your output power. You have your fundamental, the amplitude of the fundamental tones, and this is your IM products. So, when you actually increase the amplitude of your tones in your system, this is given by 20 log say A, proportional to A, but this is proportional to A cube. So, when you increase your tone of the fundamental amplitude of the fundamental frequencies in your system, the amplitude of the IM products increases by 3 times. So, you have an intercept point somewhere here. This intercept point is called an third input intercept point, and this is the output intercept point. So, these are actually the main characteristics of the RF subsystems. So, let us look into the impedance matching, how we do actually the basic impedance matching of the RF systems. Let's say you have your circuit here, then RS, which is 50 ohms, this is your transmission line, load which is of 50 ohms, so now this is your circuit. The input and output impedance of your circuit has to be terminated with the 50 ohms, or the impedance must be 50 ohms, so that it has to match with the characteristics impedance of your transmission lines or characteristics impedance of your system. So, this is actually done by adding a circuit here. You have a matching networks which has a characteristics impedance of 50 ohms, that has to be added here for the proper optimization of the power. Power optimization, then you have to eliminate any radiation, ringing, or for the good noise behavior. So, let us see how the matching is done. Let us see for the simple transistor amplifier with a capacitive input, how do you actually match the impedance. Let us say it is having something like 50 ohm J30. So in order to match this network, in this way you have a characteristics impedance of 50, because the impedance of the inductor is cancelled by the impedance of the capacitor. Here you can see the impedance of the inductor is cancelled by the impedance of the capacitor. This is the simple matching network for the transistor amplifier to cancel the input capacitance. So in the similar way you can also so normally for an circuit where you have an imaginary impedance involved, let us say you have R plus some j x, this has to be matched with R minus j x. So this is normally done for impedance matching in RF circuits. So coming to the basic transceiver architecture of the, we will see the basic transceiver architecture. You have an antenna, let us say you have an duplexer here, okay, we will make it as a switch. So you have an then you have a mixer, then you have an power amplifier, then you have an so this is actually the basic architecture of the transceiver. So you have an antenna from where you either receive or transmit the signal with the help of the duplexer. So the duplexer is actually can be a simple switch or a filter. Let us see the receive part. So you have a signal coming to the receiver, where you actually take the signal, filter it, the outband signals are filtered out so that it does not overload the low noise amplifier. So the low noise amplifier actually amplifies the signal, because the input signal is very weak, so it has to be amplified without corrupting it. This job is done by the low noise amplifier, where the signal is amplified with minimum noise added to it. So this signal is given to the mixer, where the RF frequency is converted to the IF by mixing it with the LO. The desired frequency is given by the intermodulation products. This IF frequency is again filtered for any spurious signals in the IF range. So after filtering it, this has to be given to the normal baseband processing or digital processing. The DSP processing is done here, and after the DSP processing, you take the transmitter part, the modulation and the filtering is done here, means the A to D conversion is done here, and after the A to D conversion, the IF frequency which you have got from the receiver is back converted to the RF, and the RF frequency is given to the power amplifier, because in order to transmit the signal in a medium which is lossy, you have to amplify the power of the signal with the help of the power amplifier. This after this, the power amplifier signal is given to the antenna, and this is actually the basic transceiver architecture.